Hey guys, in this video we're going to talk about the effects of buoyancy. As you can see in this picture here, this object, or rather this duck, is floating in water. So what are the factors that we need to consider when we want to calculate the buoyancy of something? Okay, so there are a few factors that are involved here, which is the object itself and also the liquid or the fluid that we are going to float it in. Okay, so basically how buoyancy works is explained in this diagram. So we have gravity, which is going to cause the weight of the object. Okay, the force due to gravity, or the weight, which you know is from mg, mass times gravitational acceleration. So obviously gravity is acting downwards and buoyancy is a force, and the magnitude of this buoyancy force, or the buoyancy, is the same as the magnitude of the weight of the object. Okay, so we have the object with its weight going downwards, and we have buoyancy force pushing upwards. So here, of course, we also have an immersed volume, which you can understand when you jump into a pool, all the water splashes away or it moves out, all right, to make room for you. So that volume of water that splashes out is equal to the volume of whatever part of you that are in the water. Okay, just like as it's shown here. So the volume, not the entire boat is in the water, only a part of it. So the volume of water that is displaced or that is moved away is the same as the volume of the object that is currently underwater. Okay, so like I said, buoyancy is equal to the weight of the object. Okay, this is a very useful information. Archimedes' principle also states that the buoyant force acting on a body immersed in a fluid is equal to the weight of the fluid displaced by the body, and it acts upwards through the centroid of the displaced volume. So basically we've discussed about this. The new thing here is that the buoyant force is equal to the weight of the fluid displaced by the body. So remember the water that splashes away when you jump into the pool? So the weight of that fluid is equal to the buoyant force. Okay, so not only we have this similarity, buoyancy equals to weight of object, we also have the weight of the displaced fluid. Okay, so the question now is, can all objects float on water? So I think you know that the answer is no. Okay, what determines whether an object floats or not on water, or in fact any fluid, is the densities of. So for example, let's say we have this fluid here. Okay, this is the surface. You can see that there are three objects with different level of buoyancy. Okay, so first we have the object that is floating naturally. So the density of this object is less than the density of the fluid. Okay, this is the density of the fluid. And a suspended body, which is neutrally buoyant. Okay, it's just suspended in the water. It's neither floating at the top or sinking at the bottom. So that means that the density of the object is equal to the density of water. Okay, and then we have the sinking body, which obviously has a higher density than the density of the water, of the fluid. Okay, so the densities, comparing the densities will tell you whether an object will float in a certain liquid or not. So this diagram shows a cross-section area of a vessel. Alright, and you can see that at the bottom it has a certain shape and it has a very long draft. This part is called draft. Okay, draft is referring to the vertical length of a floating body that is suspended underwater. Okay, because sometimes we can change the density of an object in order to adjust its level of buoyancy. Just take these three things. So maybe the object is naturally uh, buoyant in water. So you want to make it lighter. You want to make it float. So how to do that is by reducing the density, of course. So how to reduce the density of an object? You just blow it up. Make it bigger in volume, but it will have the same mass. Therefore, its density will reduce. So this is what the draft is about. Okay, in some application, the draft can be adjusted, can be made smaller or bigger in order to manipulate the density of the object. So you can get the object to float more or float less. Okay, so remember, draft is the part of the object that is underwater. So that's basically it for buoyancy. We can go through this question. A rectangular pontoon has a width of 6, a length of 12, and a draft of 1.5. Remember draft, the part underwater. In fresh water. Fresh water is just water with density of 1000. So what is pontoon? You might be wondering. I have a picture here. Okay, this is a very large pontoon. Basically a square, a floating dock. Okay, normally it's in rectangular shape or square. Okay, so this is a pontoon. Just imagine this is 6 meters, this side is 12 meters, and the part that is underwater is 1.5 according to this question. So you have to calculate first the weight of the pontoon. This equation before, the three things are equal here: the weight of the object, the buoyancy force, and the weight of water displaced. So in this case, we can't find the weight of the pontoon from its mass. We can't find the buoyancy force, but we can find the weight of the water displaced because we know how much volume of the object is currently underwater. Alright, so we can calculate that, and that will give you the weight of the water displaced. So weight of water displaced is equal to the volume of the water displaced, which is what we can find from the given information, times the density of water times gravity. Okay, so volume of the water is equal to the volume of the pontoon that is underwater. So its area, 6 by 12, times the height underwater, 1.5, times density times gravity. The answer is 1059.5 kilonewtons. Okay, if you're wondering where this equation is from, it's simply weight is mass times gravity, right? And mass is volume times density. Okay, density equals to mass over volume, so you will work it out from there, and times gravity. Okay, next, what is the draft in seawater? So we have the same object. It has a certain weight which we have calculated, and this object will float on water with a draft of 1.5. Okay, so if you put the same object in seawater, will it have the same draft? Obviously not, because how an object floats or how much the draft is depends on its buoyancy in a certain fluid. So you change the fluid, in this case you change it from water to seawater, of course the buoyancy will be different. Right, so we use the same information that we have from part 1, which is the weight of the pontoon. This is equal to the weight of water displaced. So obviously this amount of seawater that is displaced will be the same as well. Alright, and this is equal to the same equation, but this time for seawater. Okay, so it's the draft that we don't know, therefore the draft will affect the volume, and the density is known, gravity, and then you can calculate the draft. So you can see that in seawater, the same pontoon will float even more. Okay, the part that is underwater is less than the draft in fresh water. It means that seawater has a higher density, therefore objects can float more easily. So if you have ever gone swimming in the ocean, you will know that this is true. Okay, it's easier to float in seawater compared to fresh water. Okay, and the last question is, what is the load that can be supported by the pontoon in freshwater if the maximum draft permissible is 2 meters? So before this, we only considered the pontoon being empty. Okay, there's no other load on it. So here we need to calculate what's the maximum weight that you can put on the pontoon so that it only sinks by 2 meters. Okay, so first we need to calculate the total load when the pontoon is sinking by 2 meters. So for a 2 meter draft, we calculate the buoyancy force, the same equation. Then we have 1412.6 kilonewtons. Here we switch the value of draft to 2 meters. So we get a new buoyancy force compared to here, because here the draft is just 1.5, here is more. Okay, just by adding draft of 0.5 meters, you can have almost 400 kilonewtons more of load. Yeah. So this is how much upthrust available, or how much buoyancy force available. But this is not the answer. You have to find the load that can be supported. So of course you have to consider the weight of the pontoon. Okay, so the weight is here, so we minus, okay, total weight minus the weight of the pontoon. This is how much load that you can put. Okay, so that wraps up your chapter 3. Please stay tuned for any more practice questions for this topic. Okay, the topic of buoyancy. And the next class, or next week, in week 5, we're going to start chapter 4. And I hope you are getting ready for your test 1.